Hello students, welcome back. Let us now begin section 2 of this notebook, orthogonality. Here's a definition. A pair of vectors v and w are said to be orthogonal if the scalar product is 0. You can write it like this using the triangular bracket notation, which our textbook author is using, or you can use the dot product notation, which we had been using from trigonometry and precalculus. Speaking of trigonometry and precalculus, please remind yourself that we used to define the dot product like this. Magnitude of v times magnitude of w times cosine of the angle theta. Remember? Of course, I changed the notation a little bit. I changed those magnitude into double absolute values because that's the notation we are using here in linear algebra. The key thing is cosine of theta here. In trigonometry, the key deal was the trigonometry, of course, so the cosine of theta was important. No wonder we used to define the dot product like this. But this is a little bit problematic in the abstract setting because we may not have the well-defined angle concept here. So how do you extend this idea into a little bit more abstract space? We do it this way. Set this one equal to 0. Then what do you get? This is equivalent to what? V times w times cosine is equal to 0. Therefore, v is equal to 0, or w is equal to 0 vector, or cosine of v is equal to 0. And what do you mean by cosine of theta is equal to 0? That's equivalent to theta is equal to pi over 2, the right angle. When v and w are non-zero vectors, then we have to have right angle. In this case, we say these two vectors are perpendicular. So the orthogonality concept is slightly more inclusive because we are allowing zero vectors as well. But I'll probably end up mixing those up, whether it is my intention or not. So if I say perpendicular, please regard it as orthogonality and vice versa. So they all mean the same, and please regard them as just scalar product is equal to 0. And if you use this expression, this definition, then you can use the orthogonality even when we do not have well-defined the angle concept. Okay, so much for the definition, and let's go ahead with an application here. And the very first application is the simplest and the most important one, the Pythagorean law. Now, if you have a right triangle, then clearly hypotenuse squared is one side squared plus the other side squared. That's great. But then again, what if we do not have right triangle? If it is obtuse triangle or acute triangle, of course, this is going to be false, but what I'm talking about is the kind of situation that you cannot draw any triangle at all because the space is too abstract. Can we still consider orthogonality? Yes, we can. Then under that orthogonality, do we have this Pythagorean rule? The answer is yes, and we can prove it using the definition of the orthogonality. How do we do that? Turns out it is a lot simpler than the proof of the Pythagorean theorem in Euclidean geometry. All you have to do is put everything into the definition of the norm, and the norm squared is the scalar product of itself, and from here we just FOIL it out. First, outside, inside, last. If you do that, you'll see the middle terms are zeros because v and w are perpendicular, orthogonal. So we end up with the right-hand side as these two zeros drop out. That's the proof, just one-liner. Next concept, orthogonal complement. Okay, this is a little out of place, but let's talk about it as briefly as possible. Given subspace W of a vector space V, we can define a certain set called W perp like this. Set of all vectors V in the vector space capital V such that V is perpendicular to every vector W of the subspace capital W. If you define it like this, then it'll turn out this W perp, capital W perp, is also subspace, and you can prove it. The proof is left to the students. Oops. The proof is left to the students. It's not going to be too difficult. Just use the common idea. 0 is in there, close under addition, close under scalar multiplication, that kind of thing. Okay, let's go over to the next topic. The next topic. Parallel and orthogonal component vectors. What am I talking about? Let's go to a visualization. That's going to be really helpful. We start with an arbitrary non-zero vector W, the red vector. All right? And given this W, we take arbitrary vector V that may be zero vector, but if it is zero vector, then that's too trivial. If it is a non-zero vector, then you have this kind of picture. It can be decomposed into green and brown, where green is parallel in W direction and brown is perpendicular. Add them up, then we should get this V, as you can see from this rectangle. Now, how do we get this green vector, the parallel component vector, P of V in W direction, and this brown vector, orthogonal component vector, O of V in W direction? It turns out we have this quantity, C equals to V dot W over W dot W. I better expand the font a little bit because we have fraction here. This C will give you the parallel component vector. You see, the green is in W direction, so it is parallel to W, so it has to be a scalar multiplication of W. When is something times W, and that something is this C. V dot W over W dot W. It is called a parallel component. Now that parallel component will give you the green vector, which is the parallel component vector, and V minus that is brown, that's the orthogonal component vector. Now before we prove it, let's consider the trivial case and then eliminate that. The trivial case when V is equal to 0, then we can simply take C equals to 0, and this one just drops out, and what do you get? V is equal to 0 vector, and 0 vector is perpendicular to everything, so yeah, it works out. And if you look at this formula, V is 0 vector, remember, so 0 times something, numerator is 0, so C is 0, everything works out. So even for 0 vector, it works out. Of course, the proof is for non-zero vector, because 0 case is trivial. Alright, so much for background, and let's go ahead and prove it. And this proof is not that important, so I'll just go ahead very, very quickly. So okay, and V minus CW is perpendicular to W. Let's begin with that assumption. Alright, so V minus CW dot W is equal to 0. What do you mean by that? Break up this parenthesis, then V dot W minus C times W dot W is equal to 0. So flip this part over to the other side and divide by this W dot W here. Then you're going to get C equals to this quantity, V dot W over W dot W. It is just the solution of this equation with respect to C. No problem there. Now, vice versa, conversely, we begin with C equals V dot W over W dot W. Yeah, we can do that because W is non-zero, denominator is not zero, so everything is okay. And put directly into this, V minus CW, so this thing w, and then work out. Break out the parentheses, and then simplify this denominator and that one out. And what do you get? V dot w minus v dot w, that's 0. So we have orthogonality as desired, and that's it. Either way, it works out. But this proof is quite possibly one of the least important proofs, so I don't worry too much about it. Now let's go over to something important. Some people call it Bessel's inequality, but I'm not exactly sure whether it can be called like that. Anyway, here we go. Let V be a vector space with a scalar product, and U1, U2, U3, U4, all the way to Un be mutually perpendicular unit vectors. So they're perpendicular, so kind of like this. Ui dot uj is equal to 0 whenever I and j are different. And when they are the same, dot product of itself is norm squared, and this is unit vector. So the norm is 1, so norm squared is equal to 1, so we have this. 0 whenever I and j are different, 1 when I and j are the same, and this thing, this expression, is often abbreviated into delta ij for simplicity. So this whole thing and delta ij are actually the same thing. It'll turn out quite useful in higher level algebra and linear algebra. I don't know how often I'm going to use it. It is called Kronecker delta. Named after German mathematical Kronecker, who lived in late 19th century. Anyway, ui dot uj is 0 whenever I and j are different, and 1 if I and j are the same. And then ci is a parallel component, v dot ui over ui dot ui. Then c1 squared plus c2 squared plus all the way up to cn squared is less than or equal to norm of v squared. And that's called Bessel's inequality. As a matter of fact, Bessel's inequality is a special version of this for some Fourier coefficients, but I'm not going to go there. Anyway, a good visualization is here, and this is a maybe not trivial case, but so simple that it may not do a great justice. 2D case is the only thing that you can clearly see, so let's do 2D. So we have V and just U1, so you don't have any of these. You don't have any of these. You don't have any of those. And can you see C1 squared is less than V squared? C1 squared is this one squared. And V squared is hypotenuse squared. Which is longer, hypotenuse or side? Hypotenuse is longer, of course. So this is hypotenuse, this is 1, and then this is perpendicular. This is parallel component and orthogonal component. So this is hypotenuse. So hypotenuse is longer than one side. And that's why this holds. But this doesn't do total justice to this theorem because I don't see any of those. So it's you may think it's a bit too simple. So let's go one step further, just one step further, that is 3D. And here we go. So we have C1 and so we have U1 and U2. So we have C1 and C2. We don't have any of those. You can still see things going on here. V is this. And then U1 and U2 must be somewhere here, there, in whatever direction. And then we have this parallel component, and then orthogonal component. And then if you take the parallel and orthogonal components with the original, we have a right triangle. So even though we started with three-dimensional case, we can drop it down to this planar geometry given by this right triangle here, and it works out. And this green is C1 squared plus C2 squared. And if you expand this idea into higher dimension, then you can introduce C3 squared and then C4 squared. Eventually, you're going to get that. You can use you can use mathematical induction if you want to. That may be a bit overkilling. In any case, that's a geometrical interpretation of that. But then again, in some cases, geometry is too hard. It's better to use the algebraic approach. And this is what we are going to do. Okay, here we go. For each I, please note that v minus c1 u1 plus all the way up to cn un dot ui is equal to 0. And by the way, this is the orthogonal component. V minus c1 u1 plus cn un. This is a parallel component vector. And then v minus that's total thing is orthogonal component vector. Dot product of ui. And then let's just work it out. Break up the parentheses. And what do you get? V dot ui and c1 dot u1 dot ui, and then c2 u2 dot ui, c3 u3 dot ui, all the way up to cn u1 dot ui. Now all those ui's are mutually perpendicular, so everything becomes 0. u1 dot ui, that's 0. u2 dot ui, that's 0. u3 dot ui, that's 0. All 0 except ui dot itself. So this is the only thing that survives. Everything else becomes 0, so drop all those zeros out. And then the ci is, well, v dot ui over ui dot ui. That's the parallel component. And then some further simplification. This denominator and then that cancel each other out. And what do you have? V dot ui minus V dot ui, that's 0. So what did you get? This thing times ui is equal to 0. This one, by the way, is orthogonal component. And then let's go just one step. This times ui is equal to 0, so multiply by ci, that's ci times 0, so that's 0. Why did I multiply the ci? I'll explain later. So in any case, this time ci ui is equal to 0. Okay, all right. And then we're going to put all the indices together. V minus c1 u1 plus c2 u2 all the way up to cn un, the orthogonal component. Dot product of c1 u1 plus c2 u2 all the way up to cn un. And what do you get? c1 u1 dot product of this. And as you saw before, that's 0. Next term, c2u2 dot product of this. That should be 0. We just saw that. Repeated, 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 and here's the last term. cn un dot product of this. That too is 0. We saw it for each I. Consequently, this is nothing more than a bunch of zeros added together. So it's 0, and the conclusion follows. The orthogonal component vector, this, and this parallel component vector, those are orthogonal to each other. As a matter of fact, that's why it can't be called orthogonal component vector, as a matter of fact, because of this orthogonality. Now, how is this useful? Here we go. V norm squared is V minus this red plus red. And then we can separate like this, and we have this equality because of this Pythagorean theorem. These are perpendicular, that's why we have this equality here. Hypotenuse squared is one side squared plus the other side squared. Now here, drop this. This is non-negative term, 0 or positive, so drop it. We're going to be able to decrease it a little bit. And then we use Pythagorean theorem again, because u1, u2, all these are perpendicular to each other. We get this equation and some further computation. We get c1 squared, c2 squared, all the cn squared. That completes the proof.